Hello everyone, welcome back. We're going to be starting Chapter 3 material today. And Chapter 3 takes a little bit of a departure from the material in Chapter 2. Chapter 2 is all about setting up the definitions of motion, deriving the kinematic equations, and then jumping into a number of example problems with moving objects, falling objects, etc. But everything that was covered in Chapter 2 dealt only with one-dimensional motion. In other words, we could only move back and forth on a straight line. In the real world, we're going to have objects that are moving in 2 dimensions, 3 dimensions, etc. And so we're going to have to figure out how we can apply that kinematics to more than one direction at a time. And for that, we need some knowledge about vectors. And so this is what Chapter 3 is all about. We're going to be covering all the aspects of vectors, including the definitions, components, and how we can add and subtract vectors, along with how we can multiply vectors together if the situation calls for it. So a vector is actually one of 2 different quantities that can be measured. The other one is what we call a scalar. And what both of these quantities have in common, they both have what is known as a magnitude. And this is a word that we may have even seen show up in the Chapter 2 material. And so what we need to realize here is that magnitude really just means the absolute value of the quantity. And so if we have some value of x, then the magnitude of x would be the absolute value. So in other words, if x was equal to 5, then the magnitude of x would equal 5, and that's not surprising. But if x equaled -3, then the magnitude of that would be +3. So what the absolute value does is, from a mathematics perspective, it measures how far from the 0 point on the number line your value happens to be. So whether we were at +3 or -3, each of those values is a distance of 3 units from the origin. So whether it's positive or negative, that doesn't matter. We're just taking the absolute value. And so both of these terms will have magnitudes. And for us, the magnitude is basically just going to equate to the number that is assigned to that measurement. What makes these two different is that a vector also has to have a direction associated with it. So a vector is some measurement that not only has a numerical value, but we also have to assign a direction to it. For a scalar, we have just the magnitude, or magnitude only. So a scalar is something that you're going to measure, but it does not require a direction. And to help us with that idea, what we're going to do is we'll go ahead and just put together a collection of different terms that would be considered either a vector or a scalar. And we might as well start with the terms that we defined back in Chapter 2. The first term that we had was position. So position was a physical location as measured with respect to a reference frame. So what this tells us is that we have some kind of reference frame with a 0 point, and then we have to measure from that 0 point out to that location. Well, as you can see, to get from the 0 point out to that location, it required us to travel to the right, or in this case, if we were using the X notation for a horizontal axis, we would have to measure in the positive direction. And then if we change our position, if we move to some other location, that's what we called displacement. Well, as we can see, that also requires a direction. We have to move from one point to another, and in this case that required us to move to the left or in the negative direction. So we can insert these two terms into our vectors collection because both of them require a direction. But if we keep going with our definitions from the previous chapter, after displacement, the next definition in line, not vector, velocity was the next term in line. But velocity was defined as displacement over time. Now we already know that displacement is a vector, and so now we're trying to make a new term using a vector. Does that mean that the new term becomes a vector? And the answer is yes, because our displacement is a vector, but our time, well, if you think about measuring time, does time require a physical direction to be paired with the numerical measurement? And the answer is no. Time does not have a physical direction that it points in. We do have a tendency to think of time as moving forward or flowing forward, but in the physical sense, it does not have a direction. And so what we have here is a vector divided by a scalar, and that is going to make another vector. So we'll go ahead and add velocity to the vectors group, and we can put time in with the scalars. After velocity, we had acceleration, which was defined as the change in velocity with respect to time. So if velocity is a vector, we are again dividing by a scalar, and so we're going to get another vector from that. And so our acceleration will also be a vector. Now, looking at those 5 terms, these are essentially the 5 entries that we have been using for all of our kinematic equations. And 4 of the 5, it turns out, are vectors. And so they require some kind of direction to be associated with them. Time is the only one that's not a vector. And so what we're going to have to do is we're going to have to figure out some way of distinguishing between a vector and a scalar when we start writing out any of our mathematical expressions. But for right now, I just want to produce a few more examples of vectors and scalars. So if you take a moment, just kind of brainstorm, think of different things that can be measured. I mean, there are a lot of things out there that can be measured, but how many of those require some knowledge of physical direction. And since we're kind of lacking in the scalar area, I'm going to go ahead and put in a few more examples here. One value that can be measured that doesn't require a physical direction is temperature. Another one that we can have, which is going to show up in chapter 5, would be the mass of the object, or how much material that object carries with it. Another one could be volume in the three-dimensional sense. And then if we start combining some terms like mass divided by volume, that gives us a term called density. And so density does not have a physical direction that it points, but it is something that can be measured. Some other things that could be vectors or scalars. Also, when we get to chapter 5, we're going to start incorporating force into the mathematics. So when we apply a force, it has to be applied in a certain direction. We can have momentum. Momentum is also going to be a vector. Momentum is actually a combination of mass and velocity, but as we've seen down here, when we start combining vectors and scalars, we just end up producing another vector. Something else that we can put into these collections, energy would be a scalar. Energy does not require a direction. And related to energy is a term called work. So work is the ability to transfer or transform energy in a system, but it does not have a physical direction associated with it. And let's see what else we have. I'm trying to think of anything else that might potentially pop up during the course of our course discussions. Let's see, when we get to the last chapter in this course material, we're going to start talking about rotational systems, and so torque is basically the force equivalent for a rotating body. And then we'll have something called inertia, which will be a scalar. And so these terms right here, I would say with the exclusion of the temperature term, we're going to see all of these terms show up at some point during this semester. Temperature is not really something that plays a big part in the dynamics or the motion of the object, but when we get into Physics 2 or into thermodynamics courses, obviously then the temperature is going to play a big part. So those are our examples of vectors and scalars, and there, as I said, are going to be plenty of additional examples of both. It just depends on how far we're willing to take things, and for different classes that you're going to take in the future, you're going to run into additional vector terms and scalar terms as is appropriate for that course material. But for now, we need to figure out how are we going to distinguish between a vector and a scalar in our written work. Well, as you can see, I was using these arrows to indicate the direction that our measurements needed to be made in. And so for our vectors, we are going to adopt that notation of using arrows. We're going to use the arrow. The tip of the arrow will indicate the direction that that vector quantity needs to point in. But that only takes care of the direction of the vector. How do we take care of the magnitude of the vector? How do we take care of the numerical value? Because certain measurements will be small, other measurements will be large, some may be medium. And to take care of that, what we do is we just draw vectors of different sizes or different lengths. Now this can get kind of tricky if you're trying to be exact in your drawings and you're trying to be exact in the measurements of the lengths of these arrows and the directions that they're pointing. That's gonna become pretty demanding in terms of your drawing skills and how accurate you're able to make these drawings. For me, I typically just have a habit of freehanding the drawings. In other words, these are more akin to just a sketch to give me an idea of what is happening, but I don't want to rely on these sketches to tell me what the final answer is. What I am going to do is I am going to rely on the math to tell me what the final answer is. So these arrows, these will, don't get me wrong, they'll be very helpful in visualizing what is happening in these systems, but eventually we want to wean ourselves off of having to draw every single vector system. Instead, if we can set up the math right away, and if we have a solid grasp on the mathematics of the vectors, then the math will give us an exact answer, and we don't have to worry about any of the guesswork that comes from the drawings or the sketches. Well, what about our mathematical expressions? How do I know if a given value is a vector or not? So for that, what we'll do, let's say that quantity A is a vector. The way that I will know that is that we will have a little half arrow hat hovering right above that term. And so what this does is it tells me and anyone else who's looking at my work, this quantity is a vector. As such, it should have two pieces of information, a magnitude and a direction. And so what I can do now is I can say vector A is a vector that measures a length of 5 meters, but that's just the magnitude. This doesn't tell me yet the direction that this vector points in. And since we're going to start expanding our discussions into 2 and 3D systems, we'll go ahead and draw a two-dimensional reference frame. So traditionally, X is the horizontal, Y is the vertical, and up and right are respectively the positive directions. So vector A is 5 meters. Well, starting at the origin, how many different ways could you measure 5 meters? And the answer is pretty much infinite. You would end up tracing a circle with a radius of 5 meters. And so we need to specify what direction we're going to travel in. And so I would say, well, let's go 5 meters at 30 degrees. Okay, so 30 degrees, I can measure 30 degrees, but from where? Where do I start my measurement from? Do I start from the x-axis, the y-axis? Do I measure from one of the negative axes? So we have to be very specific about where we're going to start our measurement from. And in trigonometry, we are taught that the traditional starting point for measuring an angle is at the positive x-axis, so that's 0 degrees. And then we measure in a counterclockwise direction for positive angle measure. If we measure in the clockwise direction, that is considered to be a negative angle measure. And so here I have 5 meters at 30 degrees. Technically that's a positive. And if I don't have anything here that specifies where the angle measure begins, then it is understood to be at the traditional 0 point of the x-axis. But for any other starting point of angle measure, we must indicate where we want that angle measure to start from. So I'll just go ahead and put in positive x. And so now that we know how long the vector is and where it needs to be pointing, as I said, we can kind of do a quick sketch of what this vector needs to look like. So I'm assuming that this line here is approximately 5 meters long with respect to the reference frame, and then we have our angle of 30 degrees with respect to the positive x-axis. So that's what vector A looks like. We now have a length and a direction, and we've got our sketch, but that's about it. That's about all we can do with that vector until we bring in some more trig. But for right now, let's try another vector. We'll say vector B equals 8 meters at negative 60 degrees from the negative y-axis. And technically we should put a little arrow hat, or not an arrow hat, sorry, but a caret on top of the labeling for the axes, because that indicates the axis direction that we're going to measure from. Okay, so this one, I need a vector which is 8 meters long. So whatever I draw for vector B is going to have to be longer than vector A. But now I have to measure negative 60 degrees from the negative y-axis. So I'm going to start on the negative y-axis, and then I have to measure in the negative direction for angle measure, which is clockwise. So that means I'm going to be measuring clockwise 60 degrees. So this angle measurement right here is 60 degrees in the negative direction. I'm going to get rid of this one here so we don't make the mistake of thinking that those angles are the same. I'll go ahead and put the 30 in there. So there's the angle measure. Now I can put in the vector itself. So I'll use blue here for vector B. And I've drawn it a little bit longer than vector A because the magnitude of vector B is longer. Alright, well, keep in mind that this was all a freehand sketch. My angle measures are probably not exact, nor are the are the values of the magnitudes that I've used. But again, these sketches are just there to give us an idea of what the picture should look like. If I want a more exact picture, then what we need to do is we need to let the math take over. So what we're going to do is we're going to come over here to the other side of our sketch, and I want to represent vector A, but not using the magnitude and angle description. And you might be saying to yourself, well, I thought that's how all vectors were supposed to be defined. They have to have a magnitude and an angle. And they do, but that's not the only way that we can describe a vector. So let's come over to this side, and I'm just going to draw vector A over here again. We have vector A, and actually let's use a different vector. We'll use vector C. Let's say that vector C is describing the direction that a highway travels. And so you're trying to get from one point to another point, and you see this particular highway on the map, highway C, and that highway is 50 kilometers long, getting you from your starting point to your destination. Except before you can even get onto the highway, you see that there's a sign telling you that the bridge is out, and so you can't take this particular highway. You have to take a detour. And there are detour signs that say that you can travel so many kilometers to the, let's see here, we have positive x and positive y. Usually you don't see x and y on a map. You would see east and north. And so we can very easily replace things like x, y, negative y with compass directions if we had to. And then after you've driven so many kilometers to the east, you'll turn directly north and continue until you get to your destination. And so regardless of taking the original vector C to get from the start to the finish, or if you take the detours, you're still getting from the same start point to the same end point. The only difference is that the blue arrows there might require a slightly larger or longer trip. But what this does for us, if you'll notice, I have just constructed a right triangle out of these three arrows. Vector C is now the hypotenuse of a right triangle, and I know that that hypotenuse has a value of 50. The only thing that I need now is one other piece of information about this right triangle. And since we're starting with the idea that we're going to be using magnitude and direction, well, let's go ahead and throw a direction in here. We'll say theta is 30 degrees. So vector C is 50 kilometers long at 30 degrees from, so which way did we measure? We measured from the x-axis in the positive angle direction. So we can either put positive x from, or excuse me, we can either put positive 30 from the positive x-axis, or we can put positive 30 degrees to the north of the eastern direction. We started pointing to the east, and then we followed our angle towards the north axis. Well, now that I have this information, we can let the trig take over. And back in your trig days, we all should have memorized this little saying, SOHCAHTOA. And this reminds us of how all of our trig functions are going to fit together. So sine of theta would be the opposite leg over the hypotenuse. Cosine of theta is the adjacent leg over the hypotenuse. Excuse me. Hypotenuse. And then tangent of theta would be opposite over adjacent. So we're taking our SOHCAHTOA, and I will mention right now that the opposite leg and the adjacent leg, those are always defined by the placement of your angle theta. We have our 30-degree angle in this lower left-hand corner, and so that means that this leg is the leg that is adjacent to the angle. That means that this leg is the leg that is opposite of the angle. The hypotenuse, well, the hypotenuse is the hypotenuse. It's always the leg opposite of your right angle. But now we have a way of figuring out what the values of the adjacent and opposite legs of this right triangle need to be. The information that I have available to me is I know what the hypotenuse is, and I know what the angle is. So if I want to figure out what the measure of the opposite leg is, then I need something that involves those three terms. And that is going to be sine theta. Sine theta is opposite over adjacent. Well, I'm not going to call these opposite and adjacent for very long. I'm going to call these, let's see, what were we calling our vector? Vector C. I'm going to call this the y component of vector C, because this is the part of vector C that is pointing in the y direction. Likewise, I'm going to call this the x component of vector C, because it is pointing in the x direction. Sine of our angle theta is equal to the opposite leg, which we are now calling the y component of vector C, divided by the hypotenuse. Well, the hypotenuse is 50, and 50, well, that's just the magnitude of vector C. And so what we can do is we can just say that the hypotenuse is equal to the magnitude of vector C. And there's two ways that we can denote the magnitude of a vector. One way is we can put the absolute values around the vector expression itself, or a more I would almost call it a lazy version. is just to remove the hat, the vector hat, from the vector, because right now we're not so concerned with the direction that vector C is pointing. We're more concerned with the numerical value that it has. All right, so now the algebra takes over. We can multiply each side by the magnitude of vector C. And we can plug values in. We have a magnitude of 50. And sine of our angle, which is 30 degrees, is going to produce, we can plug that into our calculator, or if you remember some of your sine evaluations, I believe this is 25. Don't forget your units. 25 kilometers. So when we look back at our little detour picture, the y component of our detour trip says that we have to travel 25 kilometers northward. Now we just have to figure out how far to the east we traveled, and that is going to be the value of our x component. For that x component, didn't want to do that. There should be a back button. There we go. Let's see if I can do that again without erasing. There we go. For the x component, we want some trig function that involves the adjacent leg, the angle, and the hypotenuse. Now, we do technically know what the y component of our triangle is, so really we could use just about any trig function, but that was a calculated value. Unless we know for sure that that value is correct, we probably don't want to use that to try and solve for another value in our system. So we're not going to take that chance just yet. We'll use the values that we were given, and those values say that combining adjacent, hypotenuse, and angle is cosine. So cosine theta equals the adjacent leg, which is cx, divided by the hypotenuse, which is just the magnitude of our vector c. We can then rearrange that by multiplying each side by the magnitude of c. We have cosine equals c of x, and then we plug all of our values in. And now we need cosine of 30. And I don't have that one memorized, so I'll go ahead and get my calculator out. Cosine of 30. And then we have to multiply that by 50. And we get approximately 43.3 kilometers. So our detour over here, since the bridge was out, we had to travel 43 kilometers to the east and 25 kilometers north, and that allowed us to get from the same starting point to the same end point as what the 50 kilometer trip would have allowed us to do. Okay, well, we said that we wanted to represent this vector c in an alternative manner. Instead of saying that vector c was 50 kilometers at 30 degrees north of east, is there another way that we could describe it? Well, there absolutely is. We now have information about exactly how far to the east and how far to the north vector C will take us. And so we can describe vector C using those components. We have this combination of the x and y components of vector C, and when we put them together, we get from the same initial starting point to the same ending point. The values that we had for those were 25 and 43.3 respectively, so we'll go ahead and put those in. And we had our units of kilometers. Now, one major issue that we're going to run into here, you'll notice that if I leave the expression like that, the first thing that you're probably tempted to do, and the first thing that someone else is probably tempted to do, is to add those two numbers together. And if you do that, you're going to get 68.3, which is not the value of vector C. It's too big. Well, these two components, each of these components lies in a different axis. We have one component that's lying in the x-axis. Sorry, I have these backwards, don't I? That's the hard part about doing an online video, is you don't have anybody to catch your mistakes for you. But okay. So our two components are lying in completely different axes. We have one component that is an x component, we have one component that is a y component. And back in algebra, if you had dissimilar terms, say you had x plus y, well, could you add those together? And the answer is no, they're not the same terms. We won't be able to add them together until we actually get values. Well, yeah, I technically have values for these, but these are not like terms. They exist in different directions. And because of that, we cannot add them together in the traditional sense of arithmetic. What we're going to do next is we're going to put in some subscripts to label these components so that we don't make that mistake of adding them together. Now, the logical thing to do would just be to put an x and y in there to label them as the respective components of that vector. Unfortunately, we're not going to do that. The x, y, and z notation, these are actually going to be saved for any variable notation that we need to include. We will, at some point later in the semester, have components of a vector that can change. Our components will be varying, or variables. So we have to save x, y, and z for that variable notation, which means we have to use some other letters that currently are not in use. So we're going to use I, j, and k. So respectively, I, or I hat, will denote anything that sits along the x-axis. J hat will denote anything that lies along the y-axis, and k hat will denote anything on the z-axis. We only have a two-dimensional vector right now, so we don't need to worry about the z components just yet, but they're coming. We will eventually have to deal with some three-dimensional vectors. But that just means I'm going to attach an I hat and a j hat to the x and y components respectively. So now I'm not tempted to add them together. But I do need a way of taking those components and reproducing the original information. So what we've done so far is we have taken the magnitude and angle of a vector and we've produced the components of that vector. And we did that with some math. We did that using some trig. Well, if we can go one direction with the math, we need to be able to go back. So I need to be able to take the components of a vector and combine those in some manner, probably using some trig, so that I can reproduce the magnitude and the direction that this vector is pointing in. Now the nice thing about having these components is that you know exactly how far in each given direction you need to go. Vector C, I have to go 43.3 kilometers to the east, and then I have to turn and travel 25 kilometers to the north. So going from the origin to that final endpoint, what is the value of the magnitude and what is the angle that our final vector is pointing at. So this is that original vector C, and I need to find a way to put those values back together to reproduce the 50 kilometers and 30 degrees north of east. Well, I have the two shorter legs of a right triangle, and we know back from trig, the Pythagorean theorem says a squared plus b squared equals c squared, and appropriately enough, c is going to be the hypotenuse of our right triangle. Now the values of leg A and leg B, those don't matter. They can be either or, just as long as they're the two shorter legs of our right triangle. I'm just going to go ahead and assign values to each of these. And so if we square the value of each side leg and add them together, we will get the square of the hypotenuse. But I don't want the square of the hypotenuse, I just want the value of the hypotenuse. So that means I need to take a square root of each side. And this is what I like to call my magnitude mantra. We have the square root of the sum of the squares. We have the square root of the sum of the squares. This is how we are going to find the magnitude of any vector. And we are going to see that word magnitude again and again and again all through this semester and probably through most of your follow-up courses, physics courses, engineering courses. You're going to see that term magnitude. And so if we go ahead and chant this little mantra, square root of the sum of the squares, square root of the sum of the squares, square root of the sum of the squares. So every time you hear that term magnitude, you want your brain to start chanting that mantra, square root of the sum of the squares. And then you will know how you're going to figure out the magnitude of that vector. So we have the square root of the sum of the squares of our components. So I will go ahead and square each of my components. 25 squared plus 43.3 squared, which gives me just about 2,500 but I need to square root that. And whenever you have a square root, keep in mind that there's the possibility of having a plus or minus solution. But for us, a magnitude, remember what a magnitude is. Where did I have all that stuff? What is a magnitude? Well, a magnitude is an absolute value. And an absolute value can only be positive. So we're just going to take the positive value. Square root of our answer is going to give us approximately, oh, look at that, 49.99889. If you don't mind, I am going to round that up to 50, because for this value right here, the 43.3, that value was cut off. We would actually have 43.33 repeating. So the more threes that you could plug in there, and the more decimal values that you can carry along with your work, the closer that this is going to be to the actual answer. But even this is well within the error range of what our online homework system would accept. But that's the first half. We have reproduced the magnitude of our vector using the components. Now we need to reproduce the angle of that vector. We do now have the magnitude of our vector, but that's a calculated value. Keep that in mind. Yeah, I know 50 was the original value, but let's just pretend for now that we didn't know that. That's a calculated value. We want to use given information, right? Right now, these are the given pieces of information that we have for this problem. I want to use those two pieces of information to solve for the angle of this triangle. So going back to the list of our trig functions, the trig function that involves the opposite leg, the adjacent leg, and the angle is the one trig function that we haven't used yet, which is tangent. So we'll come up here and we'll use tangent theta. Tangent is opposite over adjacent. Remember, your theta defines the legs of your triangle. Opposite leg, opposite of our angle, that's the 25. Adjacent leg, adjacent to our angle, is the 43.3. And this is going to give us the value of tangent theta, but I don't want tangent theta, I want theta. To get theta, I will apply an inverse tangent to each side, or arctangent, depending on how you learned the trig. And so that means that theta will be the inverse tangent of 25 over 43.3. 25 divided by 43.3. That's about 0.577. And so then we need to take the inverse tangent of that value. And we get 30.00073. And I'm just going to round that up to 30 degrees, which was exactly what we wanted. So we are going to end our video for today right there. We have learned the defining aspects of a vector. We have to have both a magnitude and a direction. We've learned that we're going to denote vectors as arrows, at least in our drawings. But then we have two different ways that we can describe the vectors mathematically. We can either describe the vectors using the magnitude and angle notation, or we can describe the same vector using components measured with respect to the x, y, z axes using the I, j, k notation. And as I said, we will eventually start dealing with three-dimensional vectors. But for right now, we want to get in the practice of taking vectors, breaking them down into their components, putting them back together. And what we've shown today is a vector that exists in the first quadrant of our xy plane. And in that first quadrant, as we can see, the x and y components of that vector are both going to have positive values. So the x and y values of that vector are both positive. If I move over to the second quadrant somewhere, in quadrant 2, well, in quadrant 2, use a different color for quadrant 2, these are what the components of the vector would look like. And the x component of that vector, well, that's pointing in the negative direction, but the y component is pointing in the positive. Down in quadrant 3, yet another color, we have x and y components of our vector in quadrant 3. In this case, both of our components are negative. We have an x component that's pointing in the negative x direction. We have a y component that's pointing in the negative y direction. And finally, we have vectors that could be in the fourth quadrant. And what color should we use? We'll use purple. All of our vectors in the fourth quadrant are going to have x components that are positive and y components that are negative. So what we can see from here, I'll just go ahead and make all of the colors so that they match up. So what we can see here is that for the different quadrants, we should be able to identify in what quadrant any of our vectors are in just by knowing what the components are. So let's say we had a vector A with component -3, +4. What quadrant would that be in? And it should only take you maybe 2-3 seconds to answer that, but this is a second quadrant vector because we have a negative x component and a positive y component, and that's only going to happen in quadrant 2. Now, one other thing that I want to bring to our attention, you may have noticed that whenever I draw most of my vectors, I usually start by drawing along the x-axis, and then I draw along the y-axis. Would it be okay to measure your y component first and then measure your x component? And the answer is yeah, that is perfectly okay. because you are still going to get from the same start point to the same end point. And you still end up measuring the same angle from your x-axis. The one problem that you are going to run into, however, let's take that vector as we've drawn it now. I still have the same x and y components, but now if you notice, your theta value is no longer inside of your right triangle. And so how are you going to relate that theta value to all of the legs of that right triangle? And there are two options that you can do. You can solve for the value of this internal angle, which I will call phi. It's not a very good phi. But phi plus theta is everything in between the x and the y axes, which has to add up to 90 degrees. And so phi would just be the difference between the two. So whatever theta is, phi would be 90 minus that. And then you can use phi inside of that triangle with all of your trig functions, your SOHCAHTOA. The other option that you can use is there's a geometric axiom back somewhere, I forget what it was called, but our vector line right here, I'll zoom in a little bit. Our vector line right here, we are measuring our angle theta with respect to that vector line. The angle on the other side of that vector is being measured with respect to a horizontal component that is lying on the x-axis. Just like angle theta is being measured along the x-axis. And so back in our days in geometry, we learned that the intersector of two parallel lines will have the same angles on either side. Well, that's exactly what we have here. The same angle theta that we measured with respect to the x-axis will be the angle of the other side of that triangle. And I'm going to backtrack here because this picture has gotten really messy. Oops, where did we go? Where did our value go? Oh, there we go. Alright. So this means that we can just move theta up into this back corner if we wanted to, and we wouldn't even have to mess with phi. But do remember, it is keep forgetting to turn my eraser off. Remember that it is the angle itself that defines the legs of the triangle. So if you were to use theta at its current location, this is right up here, the adjacent leg, and this is the opposite leg. Your angle defines your triangle, not the other way around. Okay, so I said that I was going to end this video like 10 minutes ago. I'll actually end it now. When we come back with the next video, we'll look at some more examples of breaking vectors up into components, putting them back together, but we're also going to take a closer look at the 4 quadrants, because when it comes to trying to calculate the angle that our vectors are pointing at, there comes a point where sometimes our calculators get confused and they'll give us the wrong answer. And so I want to show you how to ensure that your calculator doesn't mislead you. So I'll see you at the next video.